In this video, we're very briefly going to talk about some number theory advances in the 17th century. Um, of course, some ideas of number theory went way back. Even the Greeks did some number theory, even though they thought of a lot of things geometrically. But the work of Fermat in particular advanced number theory quite a bit in the 17th century. So let me just give you a couple of examples dealing with prime numbers. In Euclid, we find that if 2 to the n minus 1 is prime, then 2 to the n minus 1 times 2 to the n, then minus 1, is a perfect number. So Fermat looked at those things and said, okay, let's find out when is 2 to the n minus 1 a prime number. Turns out the ancient Greeks had only found 4 perfect numbers that fit this pattern. So when is 2 to the n minus 1 prime? Well, Fermat was able to prove that 2 to the n minus 1 is composite, not prime, when n is composite. So the only way you could make this prime for 2 to the n minus 1 would be for n to be a prime number. So primes of the form 2 to the p minus 1, 2 to the p, and then subtract 1, where p is a prime number, are called Mersenne primes. He was named after another mathematician who was a friend of Pascal, Descartes, also was the main person that Fermat corresponded with, and also with Pascal. So he was influential in his own right, but then also in bringing some of these French mathematicians together. Fermat's probably best known for 2 theorems, or a theorem and a conjecture, depending on how you look at it. Fermat's little theorem says if p is any prime number, then a to the p is congruent to a modulo p. That would be a modern way of saying that theorem. That theorem turns out to be very important in number theory, and it's used to build some other results later on. And then there's Fermat's last theorem, which is by far the most famous. X to the n plus y to the n equals z to the n has no integer solutions for natural numbers n greater than 2. Fermat, remember, didn't publish most of his works. A lot of them were written by hand and then sent to other people like Mersenne, for example, in letters. And he was looking at a copy of a work by Diophantus and wrote this in the margin of the book and said, oh, I found a most remarkable proof of this. Well, turns out he never produced the proof, and we've never been able to find his proof. Probably mathematicians and mathematics historians are now thinking that probably he eventually realized that his proof was not really a proof, that only worked maybe in certain cases. And but nevertheless, this little marginal statement has fascinated mathematicians throughout time, since the time of Fermat, and that has actually turned out to help generate entire areas of number theory. Entire branches of mathematics have been looking around trying to find this. This was eventually proved relatively recently, at the end of the 20th century, by Andrew Wiles. So this is using a lot of machinery and tools that have been developed over a long period of time. Um, so in any event, the thing I just want to say here is that there were some number theory advances. Many of the things that were uh, put together here were made use of some algebraic techniques to look at properties of numbers, prime numbers in particular, and so forth. And so a lot of that got its start. In many ways, Fermat helped found sort of some of the modern way of looking at number theory.